Okay, here we go. Focus. Speed. I am speed. One winner. 42 losers. I eat losers for breakfast. Breakfast? Maybe I should have had breakfast. Little brekkie could be good for me. No, stay focused. Speed. I'm faster than fast, quicker than quick. I am lightning.
Hey, Lightning, you ready?
Oh yeah, lightning's ready.
I'm American made, but like Chevrolet. My mama taught me how to ride.
What is going on, class?
Today, we're learning about energy transfers.
This is our mousetrap car. It is powered by this here mousetrap and this spring.
We built it with plywood and spacers and what are they called?
Hubs.
Hubs.
And we put straws in the holes to reduce friction.
And then we put a zip tie to hold the string.
Let's go.
This mousetrap car
Well-
sucks.
Why'd you build this mousetrap car?
Because we wanted to test this theory of ours.
Our claim is that the mousetrap car should move 24 times further than the circumference of the dowel from rest to the moment all of the string has left the axle.
Yep.
Well, why is it gonna roll 24 times further, not 25?
To find how many revolutions the axle will make, we took the centimeters of the string, which is 33 centimeters, and that's how far one axle will rotate.
And we know that for each rotation of the small axle right here, the CD also makes a full rotation. So we found the circumference of the small dowel rod and the circumference of the CD, and we divided them to find how many times bigger the circumference of the CD is, and that's how we got 24 times.
This car seems really difficult. How'd you make it?
Right here, we have this little area where this dowel keeps going straight through it, and every time that would do it, it would stop the mousetrap car so it could get stuck.
And that same dowel rod is also very curved to the left. And it keeps hitting this here wheel, and the mousetrap car stops.
And then, our third hardship of this is the string. You see? It keeps coming unraveled, and we had to tie it, and that makes the mousetrap car not go as far either.
Okay, last problem that we had is our straws that were in these holes kept falling out. And this makes our car not go as far because it's rubbing against the wall.
Yep.
Peace out.
I don't see no batteries. So how does it work?
It's not that kind of energy. You're stupid.
The different energies within physics is kinetic energy, which is in motion, potential energy, which is stored energy, and thermal energy, which is heat, and then chemical energy, which only really happens in living things. Okay, so what kind of energy is stored in the spring? It's potential energy, because whenever it's fully at rest, there's nothing, like no kinetic, no chemical, nothing. So it's potential.
And then once the lever arm is moving, then we have kinetic energy,
Because the energy transfers into the car, from the spring into the car.
and then we also have a little bit of rotational energy.
Now, what is a system? A system is basically something made up by scientists, so it's easier for them to find the energy within the different areas of they're trying to find energy.
Yep, and so basically, our system is just our car. We don't have the mousetrap in our system. And so, when our mousetrap is going like this and the spring is adding energy to our car, it is adding work into our car.
So basically, because the mousetrap isn't in our system, the car is basically at zero. So that's why we have zero energy within the initial. And then in the final, we have energy kinetic because that's in motion. And then energy rotation, which is the rotation of the wheels. And basically, another thing is that it's supposed to equal the same amount of energy.
How'd it go from 0 to a bunch of stuff on the other side?
Well, Noah, work is energy added to a system from outside of the system. An example of that would be our mousetrap.
So that's why there's zero energy over here and energy over here.
Is your claim right?
We don't know.
Let's go test it!
Oh, so tough.
What are we doing?
We're testing our car, Dakota. We're testing our car. That's right. Let's see if our claim was correct. Okay, so unfortunately, we were incorrect. Colin Curley said we were incorrect too. So
Yeah, you
we only
suck.
Hey, you shut your mouth.
Hey, Cameron, we went about 540 meters instead of 790 meters, centimeters. So we'll do our best next time.
This could be because of the friction in the ground, or it could be that our lever arm is sideways.
It is sideways.
So,
Like what else?
oh,
All right.
thank you for coming to our TED Talk.
We'll see you next time.
That's why I said